Welcome to Statistically Speaking with Dr. E, where we turn numbers into knowledge. Today I want to talk about something that shows up all around us, even if we don't always notice it. And that is continuous probability distributions, how we model things that can take on any value within a range, like time, height, or weight. Alright, let's think about this in a more intuitive way. When we talk about continuous probability distributions, we're dealing with variables that can take any value within a range, like height, weight, or time. There aren't just a few possible outcomes, there are infinitely many. Now, instead of talking about probabilities at exact points, we use something called a probability density function, or PDF. You can think of the PDF as a curve that shows how the values are distributed. But here's the key idea. Probabilities come from the area under that curve, not from individual points. And one important property to remember is that if you add up all those probabilities, meaning the entire area under the curve, it equals 1. That just reflects the fact that the variable has to take on some value within the range. Alright, now let's talk about one of the most important ideas in all of statistics, the normal distribution. You'll see it everywhere. In fact, a lot of the methods we use, like estimation and hypothesis testing, are built around it. What's interesting is that it shows up naturally in real life. Things like birth weights or blood pressure measurements often follow this familiar bell-shaped pattern. And here's something really powerful. Even if a variable isn't normally distributed to begin with, when you start combining or summing values, the result often starts to look normal. That turns out to be incredibly useful because it lets us apply all the tools and techniques we've developed for the normal distribution in a wide range of situations. Alright, let's connect this idea to something new. When we move from a probability mass function to a probability density function, we're basically shifting from discrete values to a continuous setting. Instead of asking, what's the probability of this exact value, we start thinking in terms of ranges and where values are more likely to fall. Now, to keep track of probabilities, we use something called the cumulative distribution function, or CDF. At any point A, the CDF tells us the probability that our variable x is less than or equal to A. Visually, you can think of it as the total area under the curve to the left of that point. And in real data, things aren't always perfectly symmetric. For example, if you look at something like serum triglyceride levels, the distribution is often right-skewed. That means you have a long tail to the right, which is a good reminder that real-world data doesn't always follow that nice, balanced bell shape. Alright, let's go over some key properties of continuous random variables. First, here's something that might feel a little strange at first. The probability that x is less than some value x is actually the same as the probability that x is less than or equal to x. Why? Because in a continuous setting, the probability of any single exact value is essentially 0. So including or excluding that one point doesn't change anything. Now, when we talk about the expected value, e of x, we're really just talking about the average, very similar to the mean you already know from discrete cases. We usually denote it by mu. And then we have variance, which tells us how spread out the values are around that mean. More specifically, it measures the average squared distance from mu. The standard deviation, sigma, is just the square root of that variance, which brings it back to the original units and makes it easier to interpret. Alright, let's take a closer look at one of the most important distributions in all of statistics, the normal distribution, also called the Gaussian distribution. It's named after Carl Friedrich Gauss, and it shows up all over the place in real life. Things like body weight or blood pressure often follow this pattern. And even when data isn't perfectly normal to begin with, we can often transform it so that it behaves like a normal distribution, which makes our analysis a lot easier. Now, the normal distribution is described by something called a probability density function, or PDF. This function tells us how values are spread out, and it depends on two key parameters: the mean, mu, which tells us where the center is, and the standard deviation, sigma, which tells us how spread out things are. The formula itself involves the number e, and that's what gives us that smooth, bell-shaped curve. If you picture that curve, it's perfectly symmetric around the mean. The highest point is right at mu, and as you move away from the center, the curve slopes downward evenly on both sides. There are also special points at mu minus sigma and mu plus sigma. These are called inflection points, where the curve changes how it's bending. And interestingly, if you dig into the math, you'll find that mu really is the average, and sigma squared really is the variance. Now, when we compare different normal distributions, we're really looking at two things: where the curve is located and how spread out it is. Changing mu shifts the curve left or right, while changing sigma makes it wider or narrower. So if two distributions have the same spread but different means, they'll look identical, just shifted. But if they have the same mean and different spreads, one will be tall and narrow, and the other will be shorter and wider. And finally, there's a special case called the standard normal distribution, where the mean is 0 and the standard deviation is 1. This one becomes a kind of universal reference that we use all the time in statistical analysis. All right, now let's focus on a very special case: the standard normal distribution, which we write as N01. This one is incredibly important because it gives us a common reference point. The nice thing is, no matter what normal distribution you start with, you can convert it into the standard normal using this transformation. Z equals x minus mu divided by sigma. We call this standardizing. Once you do that, calculating probabilities becomes much easier, because you can rely on standard normal tables or software. Now, one of the most useful things to remember about the standard normal is its empirical rules. These give you a quick sense of how data is spread out. About 68% of the data falls within one standard deviation of the mean, about 95% falls within roughly 2 standard deviations, and about 99% falls within a little more than 2.5 standard deviations. These are great for quick approximations and interpretation. We also use something called the cumulative distribution function, often written as phi of x. This tells us the probability that our standardized variable z is less than or equal to some value x. As you move far to the left, that probability gets closer to 0. As you move far to the right, it gets closer to 1. And right at the center, when x equal to 0, the probability is 0.5, which makes sense because the distribution is perfectly symmetric. And that symmetry gives us another really helpful property. The probability to the left of minus x is the same as the probability to the right of x. In other words, phi of minus x equal to 1 minus phi of x. This comes up all the time when you're working with probabilities. In practice, especially in fields like medicine, we often define a normal range as values that fall within a certain number of standard deviations from the mean. So when you hear something like within plus or minus 2 standard deviations, that's really describing a range where most of the data is expected to fall under the standard normal framework. All right, now let's connect all of this to how we actually compute probabilities, especially using R. If you're working with the standard normal distribution, the function pnorm of z gives you the probability that your variable is less than or equal to some value z. In other words, it gives you the area to the left of z under the curve. Now, sometimes we're interested in percentiles instead. For example, what value cuts off the top 5%? That's what we call a percentile. So when you hear something like z 0.95 equals 1.645, that means 95% of the data falls below 1.645, and only 5% is above it. In practice, we usually deal with general normal distributions, not just the standard one, and R makes this really easy. If you want the probability that x is less than or equal to some value x, you use pnorm x mu sigma lower dot tail equals true. If you want the probability that x is greater than x, you just set lower dot tail equals false. And if you're going the other direction, finding a value given a probability, you use qnorm. For example, qnorm p mu sigma gives you the value x such that the probability up to x is p. Conceptually, it's the same as taking the mean and adding a multiple of the standard deviation. Let me give you a quick example. Suppose intraocular pressure follows a normal distribution with mean 16 and standard deviation 3. If we want to know the proportion of people with values between 11.5 and 20.5, we calculate the probability up to 20.5, subtract the probability up to 11.5, and what's left is the proportion in that range. It turns out to be about 86.6%, which lines up nicely with what we expect from a normal distribution. Now, stepping back a bit, there's another important idea: linear combinations. If you take several random variables and combine them, like adding them together with different weights, you get something called a linear combination. The expected value of that combination is just the weighted sum of the individual means. And if the variables are independent, the variance is the sum of the weighted variances. Here's the really powerful result. If all those variables are normally distributed, then any linear combination of them is also normally distributed. That's a big deal because it's the foundation behind many of the statistical methods we use, like t-tests and analysis of variance. So even though this might feel a bit abstract, this idea is what makes a lot of our statistical tools actually work. If you found this helpful, don't forget to like, subscribe, and click the bell to stay updated on all things data and statistics. Thanks for watching.